In this video we're going to introduce the theory of block designs. So a block design is a special kind of matching problem which is highly symmetrical in a certain sense that we're going to spell out. So the definition is like this. Suppose you have integers v, b, r, k, lambda with 0 less than k less than v, 0 less than r less than b, 0 is strictly less than lambda. So in particular, v's got to be, k's got to be at least 1, v's got to be at least 2, and r's at least 1, b's got to be at least 2. Okay. Suppose you've got numbers like this. Okay. So a block design with parameters v, b, r, k, lambda is a matching problem. Okay, so you've got two sets. So the first set, previously the sets have been called A and B usually, but now they're going to be called V and B, just because that's kind of a traditional notation. V for varieties and B for blocks. Okay, so we've got sets V, comma B, and subsets Cj of V for J and B. Okay, so these sets Cj, they're going to be called, well, we could call them column sets as we did before, or we could call them blocks. Okay, so we've got subsets like this and corresponding sets so Rp, so that's going to be the set of those J for which P's in Cj. So this is a this is a subset of B. We get one of these for each V. So these got to match up with the numbers V, B, R, K, lambda that we mentioned previously in the following way. So the size of the set capital V, the number of varieties, is going to be equal to little v. And similarly, the size of the set capital B, the number of blocks, is supposed to be equal to this second parameter, little b. And thirdly, size of each block, Cj, that's supposed to be equal to k for all j and b. And fourthly, the size of the sets Rp, the row sets, or sometimes called co-blocks, that's supposed to be equal to little r. And then finally, for all P, if we do have any pair of varieties, P and Q, with P not equal to Q, you take the intersection of the corresponding co-blocks or row sets. Size of that intersection should be equal to lambda. Okay, so that's what we mean by a block design. Okay, so that was the definition of a block design, and I've written again the key equations at the top here. Okay, so the size of the set capital B of blocks is little b, size of the set capital V of varieties is little v. Then each block, each set Cj is of size k. Each of the co-blocks, the sets Rp, or row sets, those are of size little r. And intersection of any two distinct co-blocks, Rp intersect Rq, is equal to lambda. So this is valid when P and Q are different. Okay, so key fact that we need to know about block designs is that these numbers, VB, RK, lambda, they're not independent. There's several equations that relate them. This proposition. If there's a block design with parameters V, B, R, K, lambda, then these three equations hold. Firstly, that BK is equal to VR. Secondly, that BK K minus 1 is equal to lambda V, V minus 1. And thirdly, that R times K minus 1 is equal to lambda times V minus 1. So the proof for claim 1. Okay, so let's just put X is the set of pairs JP, where J is supposed to be a block, P is a variety, and P is supposed to lie in CJ. Okay. But remember the way these row sets and column sets are defined. P lies in CJ if and only if J lies in RP, right? I mean, in terms of the kind of chessboard diagram of that, both of these are just equivalent to saying that the square J comma P is white. Okay, so these two descriptions are different, are the same. Okay, they're just these are the same set. So we'll call this first description A, and this second description B. Okay, so description A. That gives us a way to count the size of the set X. Okay, so how do we find the size of the set X? Well, first we can choose J, and there's so J is an element of the set capital B, and set capital B has size little b, so there's little b is a number of possible choices for J. And once you've chosen J, then you have to choose P, and P is supposed to be an element of CJ, and CJ has size K. From this analysis, we see that the size of X is just BK. On the other hand, we can use description B, right? So here, the idea is we choose P first, okay, and there's little v as the number of possible choices for the element P. And then having chosen P, we'd have to choose J and RP, okay, and RP is a set of size R, so that's VR. So here we're saying that here we're choosing firstly P and V, then J in RP. And so these are just two different ways of finding the size of the same set, so they have to give the same answer. So we get that BK is VR. So that proves this first claim here. Okay. Yeah. So one fairly standard technique for proving things in combinatorics. We find a set and we analyze its size in two different ways. And then the proof for 2 is going to be similar, but let's just clean the board first. Okay, so Now let's look at the proof of the second part. Change colour, never mind. Okay, so the proof of 2, okay, so then we'll have a different set, y, so different but similar. So this is going to be the set of things J, P, Q, where again J is going to be a block, P, Q are in V, and P is different from Q, and both P and Q both lie in CJ. Okay. So this, and we'll call this description A. We can turn it around, say the same thing. And so the condition that P and Q both lie in CJ, that's to say, well, that P's in CJ, that's the same as saying that J is in RP, that Q's in CJ is the same as saying that J's in RQ, so together that's the same as saying that J is in RP intersect RQ. Okay, so so this was description A, and this is going to be description B. Okay, so what does A give in terms of for the sizes of these sets? Okay, so here here the way we're supposed to think about it, we choose J first. How many ways are there to choose J? Well, J just has to be any element of set B, so we get a factor of little b there. Then we get to choose P. P is supposed to be an element of Cj, and Cj has size k, so we get k choices for P. And then Q is also supposed to be an element of Cj, so there should be k choices, but we can't be the same as P, so it has to be, so that removes one choice, and we get k minus 1. That's from choosing J and B, then P and Cj, then Q in Cj less P. Okay, so that's one way to find the size of set Y. The second description okay, so second description, we're kind of thinking we're going to first choose P. So that's got to be an element of set capital V. So little v is a number of ways we can do that. Then we choose, that was choosing P. Then we choose our Q. Q is an element of V again, but it's got to be different from P. So that means got one fewer choices. And then once you've chosen P and Q, then we have to choose J and RP intersect RQ. But remember that RP intersect RQ has size lambda, so we just get lambda. P and V, then Q in V less P, then J in RP intersect RQ. Okay, so these answers must be the same. Okay, so that's a proof of our second claim here. BK k minus 1 is the same as lambda v v minus 1. And then so the so what we do is we're going to substitute 1 in 2. So 1 says that BK is VR, so we can change this BK here to VR. So you get VR k minus 1 is V minus 1 lambda. Okay. And as I said here, so V, part of the One of our conditions was that v is 0 is less than k, less than v, so in particular v is at least 2. So because v is at least 2, just in particular that means that v is non-zero. So I can just divide this equation here by v to get r k minus 1 is v minus 1 lambda, and that was our third claim here. R k minus 1 is lambda v minus 1. Okay, so that proves these identities between the parameters of a block design.